Right, so let's see what's going on here. This is page 10, I believe. All right, so this first one, or number 18, which is the first one on this page at least, a soccer ball was kicked with a vertical velocity of 10.47 meters per second and a horizontal velocity of 13.4 meters per second. Draw a picture of this scenario. All right, so to begin with, and what this problem is doing is kind of breaking down the whole problem into kind of some little components here for us. In reality, we could do this problem at the C and D by ourselves without actually having this sort of step-by-step thing going on here. But this being one of the first problems that we're dealing with something like this, we're going to take it in small chunks, but we want to get to the point where we can do all of this without the individual prompts. Okay, so let's take a look at this. The scenario, as we just saw, is this soccer ball that's being kicked down the field. Now, in reality, you don't just kick a soccer ball straight up or straight out. There's always going to be some sort of vertical and horizontal component. Now, we need to know both the vertical and the horizontal components if we're making an arc. So if we've got some sort of arc going on like this, and I were given like an angle, and it told me what the velocity of this ball was, I would know, okay, I've got to break it down into X and Y components. Nice thing is, though, they give it to us already where we don't have to deal with that. Okay, so we know our vertical velocity, 10.47 meters per second. We know our horizontal velocity. It's already been broken up for us. Now we got to figure out what's going on. So we're kicking this ball down the field. Eventually it's going to go up, it's going to come back down, and it's going to land somewhere over here. We don't know where that somewhere is quite yet. That's one of the things that we'll see in a bit that we are trying to figure out. So that would be considered the distance in the X direction that we don't know going this way. All right, our distance in the Y direction, we know a little bit more than just, okay, it's something, right? We know that halfway down the travel, that's where we're going to have the maximum height. We don't know what that maximum height is quite yet, but we do know that the highest height or the largest distance in the Y direction is going to be exactly halfway through the trip of the soccer ball. We know a little bit more about the velocity than what the problem is telling us. Right? We also know that the velocity at this position right here is 0 meters per second, and that stands for every single problem. So even if this velocity over here were larger, it could be 1,047 meters per second instead. Still, it would just go a lot higher, but the highest point would still be 0 meters per second. And the reason that that's true, and we've talked about this in class a number of times now, you're probably sick of me saying it, is because in order for something to go up, it's in the positive direction. When something comes back down, it's in the negative direction. Remember, velocity, we're not talking about positive like speeding up and negative slowing down. That's far from it. Positive is just one direction, negative is the opposite direction. So if velocity is positive in this direction, then negative in this direction, well, it had to cross 0 somewhere in order to get from positive to negative. Okay. The other way to think about this is if this ball continues to go up, if it didn't hit 0 here, it would just keep going on and on and on forever until it was out in orbit. Turns out I'm not in orbit, I'm back here. All right, so we know it's 0 meters per second for a variety of reasons. All right. We know our velocity in the Y direction here to begin with, so we also know our velocity in the Y direction to end with. It's the same number, just in the opposite direction, negative 10.47 meters per second. Now my velocity in the X direction is a little bit different. I actually know my velocity in the X direction at this point, at this point, at this point, at this point, every single point down here, because my velocity in the X direction is not dependent upon gravity. So it's going to remain a constant 13.47 meters per second. All right, and that won't change. So that's kind of nice. Once we know our velocity in the X direction, it's our velocity in the X direction no matter what. And again, because it's not being affected by gravity. Gravity pulls it down, not backwards or forwards. All right, so let's take a look. How did the ball, or how long did the soccer ball stay in the air for? A lot of students have trouble with, well, what formula am I supposed to use here? if I don't know my distance, how the heck am I supposed to figure out my time? Well, the thing is, because normally, remember, time is dependent on the distance in the vertical direction, or dy. So in this case, we don't know that, but we do know that there's another formula that we can use, right? For the vertical, for vertical distance, it's either this, or if we're also talking about a vertical component, it's this formula. The reason that both these ones are okay to use is because of g, and because we know gravity is in fact affecting our projectile, our object. Distance in the x direction, we don't have g or a. We don't have gravity pulling us backwards or forwards. We only have gravity pulling us down. So we can't use this formula if we're dealing with a situation where gravity is pulling on us. All right, so we know that our final velocity, I just said, is the opposite of our initial. So our initial velocity was 10.47. And we can get it from the scenario. Our final velocity doesn't tell us it, but we know it's just the opposite of our initial. We know A is negative 9.8 because that's coming from gravity, right? Negative 9.8 meters per second squared. So then we can solve for our time. All right, so I would just do negative 10.47 minus 10.47, divide that by 9.8, negative 9.8, to give me t. There's another way of doing this. We could figure from this point right here, this 0 meters per second, we could consider that our v final or v initial, and then consider this our v final, and we'd come out with a time, but it would be halfway. And some people tend to use this because it's a known velocity no matter what, whether or not we know our true final or not. That's the other way to do it. I recommend going with this way. All right, what's the maximum height the soccer ball reached? So we want to figure out what's the maximum height. Well, normally we call up height, but in this unit we call it distance in the y direction. So if we want to figure out what our maximum height is, we need to use dy equals v naught t plus 1/2 at squared. Now our distance in the y direction is associated with an initial velocity of 10.4 meters per second. So that's where I have that. Now the time is 1.07. Now let's take a look at why that is, because it's kind of weird, right? It's like, wait a second, my time is 2.14. Why the heck are you putting 1.07 here? And take a look at it this way. At this point right here, I'm at 0 seconds. At this point over here, I'm at 2.14 seconds. So if I try to figure out what my height is at 2.14 seconds, I should come out with 0, because that is in fact true. If I want to know my maximum height, we need to figure out what my maximum height is associated with the time that maximum height happens. Well, that's halfway through its flight, so that's 1.07 seconds that I'm dealing with. Here would be somewhere below 1.07, right? Up here would be somewhere between 1.07 and 2.14. Don't get caught up in these problems thinking, oh, well, I know my time, so that's my time everywhere. No, think about it in a real life scenario. It's at 0 seconds. It's going, getting larger and larger and larger from 0 seconds. Halfway through its flight, it's at 1.07. Now it's getting larger, larger, and larger from 1.07 until finally it hits the ground at 2.14 seconds. So, long story short, I'm using this 1.07, not 2.14, because 1.07 is associated with halfway through the flight, which is also associated with my maximum distance. Okay, so the second part of the formula, we know that the 1/2 stays in there. Negative 9.8 is from gravity. And again, I'm using my time 1.07 seconds because it is halfway through the flight, which is where my maximum distance is, or my maximum height is located. All right, squared from the formula. And we go ahead and do our math. 10.47 times 1.07 gives us that 11.2 or 11.20. Everything over here, remember the 1.07 is the only thing that's being squared here. It's not the entire thing. Don't get caught up in that. Some people still are. Easy fix though. So 1/2 times negative 9.8 is 4.9. 1.07 squared, I forget what it is off the top of my head, but when we multiply those two, we get negative 5.61. So I add those two together. 11.2 plus a negative is the same thing as 11.2 minus 5.61 gives me 5.6 meters. So that means that this distance in the y direction, this height, is associated with wherever a time of 1.07 was, which was right there. Again, we're using that time because we know conceptually halfway through is our maximum height and also our initial velocity there. Okay, so moving on. How far did the soccer ball travel down the field? Well, we know that it was in the air for 2.14 seconds. Now be careful because it's hard to figure out sometimes when am I supposed to use halftime, which would be 1.07 seconds, versus when do I use the full time. In this case, it would be 2.14 seconds. Again, think conceptually. Don't try to just plug it into an equation automatically. So I know I'm talking about how far did the soccer ball travel down the field. So I'm looking for something in the x direction. Well, the only formula that goes along with the x direction in this unit is my distance in the x, or my horizontal distance, is equal to velocity in the x direction times time, or just vt, velocity times time. Well, careful with which velocity we're using. It's the 13.4. The only reason I used 10.47 before was that's when we were talking about things in the y direction. And that's in the y direction, but now I'm talking about something in the x direction, and 13.4 goes with the x direction. Or velocity at 13.4 meters per second goes with the x direction. Now the time, going back to that, before I used 1.07, so why wouldn't I use 1.07 now? Well, we're talking about how far the soccer ball traveled down the field, so in other words, down the entire field. 1.07 seconds is only half the distance that it traveled. 2.14 seconds is the full distance that it traveled. So I used the 2.14 seconds there. So 13.4 times 2.14 gives me that 28.68. And again, the reason that we used a weird time, sort of half time in part C, was because we were talking about height. Maximum height is halfway through the travel, so 1.07 is half of 2.14. And the reason I used the full time, 2.14 seconds, for part D is because I'm looking for the entire distance down the field. Well, the entire distance down the field would be the entire time that the ball's in the air for. All right, moving on. Number 19. So we know that this problem's talking about a golf ball being struck with a vertical velocity of 5.56 meters per second. So that's where this comes into play. This 5.56 meters per second up and down, and a horizontal velocity of 31.51 meters per second, or 31.51 meters per second in the x direction, right? So that's where this 31.51 is coming from. Again, we automatically know that our velocity at the center is 0 meters per second because we have to go up, hit 0 just for a brief moment in time, to come back down. The hardest thing for people to understand about this 0 meters per second is they're kind of like, well, what do you mean? You mean to tell me that the ball actually stops? Yes, that's exactly what I'm saying, but it only stops for a split second. Obviously, it's not going to hang there for a long time, but it does stop very, very briefly before it ends up coming back down. And then we also know our final velocity in the y direction is the negative version of this number, right? If the initial was 5.56, then the final is negative 5.56 because it's coming back down. Remember, these negatives represent down. In the x direction, that 31.51 meters per second is the same throughout the entire path. So again, I know my x velocity here, no matter where it is, it's going to be the same 31.51 meters per second because it's not dependent on gravity. Whereas for the y direction, we're going to have to constantly calculate our velocity at every single one of these different locations if we wanted to know what that was, because it's going to be constantly changing, because it's going to be constantly being accelerated by negative 9.8 meters per second squared. All right, so let's take a look at how far the golf ball traveled. So it's pretty much the same as problem 18. The only difference is now it's not nice and it's not breaking it down for us. So how do I know to use these formulas then for this? Well, in order to tell how far the golf ball traveled, I know that I'm going to end up using this d equals vt, right? Distance in the x direction equals velocity times time, because it's talking about how far. So how far in this direction did it go? Well, I know my velocity, 31.51 meters per second, and then I get here and I'm like, well, crap, I don't know my time. But I do know that I can figure my time out, right? So let's see how we can do that. We know that our time is dependent on distance in the y direction. So if I knew my height, I could use that whole dy equals v naught y, or v naught y t plus 1/2 at squared. Well, I don't have my distance either, so how the heck am I supposed to do this? Well, remember we do have this other formula for our y components as well. Again, the reason that I know that this is for y component is because it has a, or you might like it as g. Either way, it has something to do with acceleration, which is due to gravity. Gravity acts in the up and down, or the y direction. All right, so let's see what we got here. We know that our final velocity in the y direction is negative 5.56 minus our initial. Our initial is the positive version of that, 5.56 meters per second. I know what my acceleration is, negative 9.8. Again, that's coming from gravity being negative 9.8 meters per second squared. I don't know what my time is, that's what I'm solving for, but I can now I can figure it out. So this negative 11.12 divided by negative 9.8 will give me 1.13 seconds. So I don't have to deal with cutting my time in half or doubling or anything else. This is the actual time. The reason that I know this is the actual time is because it's associated with the entire problem. The final velocity, the initial velocity. So I have my final velocity, I have my initial velocity here, so it's taking the entire path into account. All right, let's take a look at page 11 here. So it's very similar to the previous previous couple pages that we did prior to this one, a couple classes ago, but it's a good one. So a ball's dropped off a cliff that's 25 meters high. How long does it take to hit the ground? Well, we know that our distance in the y direction is the thing that time actually depends on, because remember, gravity is the thing that's going to be pulling this ball down. So gravity tells me how long that the ball is going to be in the air for, along with the height. Because if this height were taller, this distance in the y direction were taller, we'd have more time that this thing was traveling in the air for. If this distance were shorter, this height were smaller, we'd end up with the ball not being in the air as long. All right, so now let's stick some numbers to this. All right, so we know again the formula is distance y equals v naught yt plus 1/2 gt squared. I know that this is the formula for a number of reasons. Main thing being I have gravity in there, and I know gravity's pulling the ball down. I've got distance in the y direction, and that's what's going on here. I have my distance in the y direction. I have my initial velocity. It doesn't tell me in the formula or in the problem, but it does. It is implied, right? I know that I'm just dropping the ball. Well, if I'm just dropping the ball, I'm not throwing it down forcefully. I'm just starting it from zero, right? Starting in my hands, I let go, it ends up falling. So that's going to be 0, and then I can solve for my time. The other way that I know to use this formula is I've only got a couple options here, right? V minus V naught equals AT is the other option that I could have. I do know acceleration, I do know my initial velocity, but I don't know my final velocity, and I don't know my time. Well, I've got two variables here that are open. I'm not going to be able to use that formula then. Alright, so from there we just go ahead and solve mathematically. We know that our distance in the y direction is 25. Our initial velocity is 0, so this whole part of the formula we really don't even need because it's going to be 0 anyway. including 0 times a variable is also 0. 1/2 times negative 9.8, you probably have memorized by now accidentally, negative 4.9 times t squared. So we end up with 25 equals negative 4.9 times t squared. We should be able to have some sort of estimate in our heads that it's going to be somewhere around 5, because 25 divided by about 5 is 5. And we do find out that t squared is 5.1. Now, we're going to have to take the square root to get the final answer. Some people are asking, why don't I put it into my calculator this way? Sorry, that's terrible. Negative 5.1 squared. Some calculators can handle it, others can't, but realize in the end we're coming out with time. So does it matter? No. So you can just drop the negative at this point, because we're not going to have negative time. If we had negative time, then that would mean we are moving backwards in time, and you would be a multi-billionaire and win probably a whole bunch of different physics prizes if you could figure that out, as well as probably be a lot richer. All right, so at this point we want to figure out how fast the ball is going. So when it's talking about how fast is it going, we're talking about like the moment before it hits the ground. So like going down, 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 it's like the split second before it actually makes impact with the ground, because once it hits the ground and bounces or maybe just sticks there, it's going to be 0. Right, but we want to know right before it hits the ground, what's our velocity going to be. So we know our initial velocity, we know acceleration. We wouldn't be able to use this formula before, right? But now we know our time. Our time was 2.26. So now that we know our time, take our acceleration, multiply it by our time, we come out with negative 22.15. And we do actually keep the negative in this case, because remember, negative in terms of velocity just tells us what direction we're going. Well, negative is the downwards direction, so that makes sense. This would be negative because we are falling down, or the ball is falling down. Thankfully, we are not. All right, last couple here. So 21, a ball is launched horizontally from the same cliff as number 20 with a horizontal velocity of 12 now. What's the horizontal velocity right before hitting the ground? It's kind of a trick question, right? It seems like we should be doing some sort of mathematical formula here, but the horizontal velocity is going to be the same everywhere, right? If this is being launched 12 meters per second this way now, doesn't matter where I am in the path of this ball, it's going to be going 12 meters per second every single time, because again, gravity is pulling down, it's not pulling back, so that's going to be the same everywhere. What's the range that the ball lands at? So the range, we're talking about distance in the x direction that the ball is landing at. Distance in the x direction. There you go. Let's try that again and pretend that guy didn't happen. All right, so it falls for 2.2 seconds, right? We know that from before we solved up here. It's talking about the same cliff as problem 20. So we know that it's still falling for 2.2 seconds. It doesn't change anything that we're now launching it horizontally, because the thing that actually the thing that actually depends on time is the height, not anything to do with the horizontal components. So now I know my time. I know that it's 12 meters per second in the x direction that I'm firing this, and this is a formula for the x direction. Multiply my velocity times my time, which is 12 times 2.26, and I get 27.12 meters. So that means if I were actually launching the ball this direction at 12 meters per second, that I would come out with, or it would land 27.12 meters away from where it was launched. Okay, last one here, number 22. So a ball is thrown horizontally off a roof. That's 18 meters high with a velocity of 25 meters per second. So I've got it being thrown off a roof. Apparently I drew a cliff, but it's a flat roof apparently. I know that I'm 18 meters high. Alright, so this must be like a office building or something. Your house would not be 18 meters high. I know that we've got a horizontal velocity of 25 meters per second. I don't really know the distance. That's what we're trying to figure out. but I also don't know the time either, so I can't figure it out just by using my velocity here. If I knew my time, it'd be super easy. Just take my velocity in the x direction, multiply it by my time, but I don't know that. Nice thing is, though, that I do know what my distance in the y direction is. All right, my distance in the y direction is 18, so I would end up using my formula that I know for the y direction. So it's dy equals v naught yt plus 1/2 at squared or gt squared, right? Just personal preference, which one you want to use, and plug some values in. So I know 18 for my distance in the up and down, or my distance in the y direction. My initial velocity, this is a little bit tricky at first, it's 0. But you mean to tell me it's 0, but it says 25 here? Careful which one it is, right? This 25 meters per second is in the x direction only. At first, it's only going out this direction, right? It's not being pulled down quite yet when it's first thrown. And so that means at first, it's not going down, so its initial velocity is 0 in the y direction. It is something in the x, but not in the y. Times 1/2, g is 9.8 from gravity. Right? And then times squared, I don't know time yet. So we end up with 18 equals negative 4.9 t squared. And then from there, like I said, it says here, it's the same reasoning as number 21. Solve out. What's the vertical velocity right before hitting the ground? Again, this is pretty similar to one of the previous problems as well. We know if we're dealing with vertical velocity, we've got to take acceleration into account because gravity is going to be pulling us down. So that's how I know that I'm using this formula, because the other formula for velocity is this, right? Velocity equals distance over time. But where's my a? I don't have my a or a g, so I can't use this formula. All right, so we do know our acceleration, right? It's on Earth. We know that it's going to be negative 9.8. My final velocity, I don't know. I don't know my time either. So that means that I've got to figure out something to do here, right? So we do know that our time is dependent on our distance in the y direction, because gravity is the thing that's pulling me down, and it's going to be the thing that causes projectile to hit the ground eventually and stop its time in flight. So I use dy equals v naught yt plus 1/2 gt squared. I know my distance in the y direction is 18. I know that my initial velocity in the y direction is 0. I don't know my time yet. That's what I'm solving for. 0 times time is going to cancel anyway, so really I don't even need this first part of the formula. You can leave it in there if it freaks you out not to. And then we know 1/2 is part of the formula. Negative 9.8 is from gravity, so 1/2 times negative 9.8 gives us negative 4.9 times t squared. Our distance in the y direction was 18, so we just carried that down. 18 divided by negative 4.9 gives me this 3.67. That's time squared, not time. Take the square root of both, get 1.92 seconds. I went fast there because we've seen this a bunch of times before. And you can always rewind and give it another go if you need to. So now I do know my time, so I can take that time, plug it in there, and now our formula is complete. Just solve for our final velocity. So we end up with v equals negative 9.8 times 1.92. Multiply those guys out and I get negative 18.82. And it does make sense that it's a negative because this ball is being dropped off the cliff. So it's going down. It would be positive if it were going up. What's the range that the ball lands? I love these problems. They're nice and easy ones, right? Because we're just looking for distance in the x direction. We know that our velocity is going to be the same in the x direction no matter what, because again, gravity acts in the vertical direction, not in the horizontal direction. Multiply it by our time. The reason that I can use a time of 1.92 here, even though I got this value by solving an equation that's associated with the y direction or y components, I can get away with mixing this component. Because think about it this way, if I've got an object that's being dropped off a cliff or thrown off a cliff, its time is not going to be dependent on the y direction or the x direction, right? If this object is falling, as soon as it hits here, it's going to land at some time. Well, whatever that time is in the y direction, it's also that time in the x direction as well. Because it's not like one object can have two separate times for its vertical component and horizontal component. The object hits the ground at whatever time the object hits the ground at. It doesn't matter if it's y or x. So now I'm using that 1.92 from what I solved before. 25 times 1.92 equals 48 meters. All right. That was fun.